Our next big topic is about redox titrations. And so this is ultimately just stoichiometry. We are going to talk a little bit about the color changes because that are common to certain ones. The nice thing about a lot of redox reactions is that you don't have to pick an indicator the way you do with an acid-base reaction, because the actual components that we use are colored, or at least one of them is, and so we look for a certain color change dealing with the reactant, and we're good. Not always the case, but it's nice. So our first reaction is going to be using potassium permanganate. So potassium permanganate, or manganate 7, is this nice, pretty purplish color till you get it on your skin, and then it's a funky brown color. And so if we were to react it with something, this is frequently used with iron compounds. The iron compound is most likely colorless. And we add in that pretty permanganate, and as long as it's being consumed, we remain colorless. But then as soon as you add a drop and it turns a real light pink color, that lets you know that that's your equivalence point. So you've added in, one drop beyond your equivalence point. You've got a little bit of permanganate in here, and it's this nice pretty pink. And actually that pretty pink is the manganese 2 ion. So here's an example. This is our balanced reaction. And our question is, all of the iron in a 2-gram tablet, was dissolved in an acidic solution and converted to iron 2. This was then titrated with potassium permanganate. The titration required 27.5 cubic centimeters of 0.1 molar permanganate. Calculate the total mass of iron in the tablet and its percentage by mass. So guys, what we're going to do is stoichiometry. We know about the permanganate, and so we need to know the mass of iron, in other words, the grams of iron. So yes, this is an iron ion, but the mass is going to work out the same, like molar mass from the periodic table. So we'll start with our 25 cubic centimeters of the permanganate. Now, it doesn't matter if you write KMnO4 or just MnO4, because the potassium's a spectator here. So some people really, don't like to drop that potassium. Doesn't matter. Okay, so I have my volume. Now I'm going to use that molarity, that 0.1 molar is 0.1 moles for every 1,000 cubic centimeters. Now I'm going to use a mole ratio. We're finding out about iron. Now I want to know the total mass of it, so I'm going to find my molar mass on the periodic table. And then I'm going to put everything into my calculator. Okay, so that tablet was 0.3072 grams of iron. The other part that asks for is the percentage by mass. Well, remember, percent by mass is ultimately the part out of the whole. So the 0.3072 grams out of the 2 grams. And I'll multiply that by 100 to convert it to a percent. Okay. Our next version of a redox reaction involves iodine and a compound known as thiosulfate. So this reaction actually doesn't change color, but here we use a starch indicator because starch and iodine forms this dark purplish blue. So here's the reaction that we do. We react the iodide ion with whatever oxidizing agent or thing that we want to measure, and it forms iodine and then the reduced product. And then we titrate that iodine with the thiosulfate. And so we can kind of reverse engineer it. Okay, here's an example. And, well, let me go back. And we have starch sitting in our solution so that the moment we have excess iodide ions, we get the dark bluish purple color. I think we had some people last year who titrated bleach, some people who titrated vitamin C. Both of these can be done with iodine, so you use that starch indicator. Okay. A household bleach is an oxidizing agent that contains sodium hypochlorite as the active ingredient. It reacts with iodide ions in acidic solution as follows. So here's a reaction. A 10 cubic centimeter of bleach was reacted with a solution of excess iodide ions, and the liberated iodine was then titrated with sodium thiosulfate. The titration required 38.65 cubic centimeters of 0.02 molar sodium thiosulfate. Determine the concentration of hypochlorite in the bleach. So we actually have two reactions going on. We have this one, and then we titrate this iodine using the thiosulfate. So we're going to start with our thiosulfate and figure out how much iodine it reacted, and then we're going to use a second mole ratio to go from iodine to hypochlorite. So I'm going to start with my volume of thiosulfate, and I'm going to use my molarity, 0.02 moles per 1,000 centimeters. Okay, and iodine is the thing that's in common between these two reactions, right? So I'm going to use a mole ratio between thiosulfate and iodine, and then a mole ratio between iodine and hypochlorite. Now you could ultimately just simplify this and just say, well, it's a 1 to 2 mole ratio of thiosulfate, but just be careful if you do that sort of thing. So I can find out my moles of hypochlorite. Now I want to know the concentration, in other words, the molarity, or the moles per cubic decimeter. Well, we titrated 10 cubic centimeters of bleach, so 0.01 liters, or cubic decimeters. So I'm going to divide my moles by my liters and get the molarity. The other redox titration that you need to be familiar with, or just know is common, is to use the dichromate ion. So dichromate is orange, and as it's reduced, it turns to the chromium 3 ion and becomes green in color. And so it's a pretty little color change. And this is used in breathalyzers very frequently. And you can measure the percent light transmittance that's different between the orange and the green, and from there extrapolate someone's blood alcohol level. Okay, but here's our application for today, the Winkler method and biological oxygen demand, or BOD. It's a good way to measure water quality. And what it does is it measures the amount of oxygen needed to oxidize organic molecules over a period of 5 days at a specified temperature. So there's your official definition of biological oxygen demand. Now I want to say organic molecules. We're talking about not organisms that are still in the water, but various molecules, for instance, waste. And a low BOD means there's poor water quality. There's not a lot of oxygen. So you take an oxygen sample out of or a water sample out of a river, pond, whatever, and you incubate it over the 5 days, and you measure the oxygen demand before and after. Okay, so there's a couple steps here. You use oxygen gas as an oxidizing agent to convert manganese ions into manganese 3 ions. And then you use a precipitate, or you precipitate that out and you do titration. So anyways, here are actual equations. And this is our precipitate that we're looking for. Notice that we react it with iodine. So then we'll react the iodine with the thiosulfate. Okay, so we measure this against the thiosulfate. Notice that there's a 2-to-1 ratio of the thiosulfate to the iodine. But we're wanting to know oxygen. Well, if we work backwards from iodine to this precipitate, that's a 1-to-1 ratio. And from the precipitate to oxygen is a 2-to-1 ratio. So this bottom one is what I would write down. The ratio of oxygen to thiosulfate is 1-to-4, the mole ratio. So here's an example. A 500 milliliter volume of water was reacted with the reagents in the Winkler method. 9.5 milliliters of 0.05 molar sodium sodium thiosulfate was needed to react with the iodine produced. Calculate the dissolved oxygen content of the water in parts per million. Okay. So we're going to start with our volume of the thiosulfate, and then we'll use our molarity to get to moles. We'll use that mole ratio we just talked about. And parts per million, if you think way back, is mass-based, so we're going to convert this to grams of oxygen. We'll figure out we had 0.00038 grams of oxygen in the solution. Okay. By the way, you'll be given the equations. You don't have to have those equations memorized, but it's nice to have already seen that the mole ratio is 1:4 to simplify it, so you don't have like 5 mole ratios in here. Okay, so we have our grams of oxygen. We want to know parts per million. Well, here's our formula for parts per million. It's the mass of the component, here oxygen, over the total mass of the solution, and then we multiply it by a million. Well, mass of the solution. We can assume that density of water is 1 gram per milliliter. So if we have 500 milliliters, we have 500 grams. So we have our mass of our component over the total mass of the water plus the component. We multiply that by a million, and we get 7.59 parts per million. And here's a nice little range of parts per million and how that affects your aquatic life. All right, there you go for redox reactions and titrations.